So in this lesson, we're going to try and improve our theory on trigonometry so that it will work with any angle of any size we like. So with the trigonometry we have been doing so far, notice how it's all been done with right angle triangles. And these equations only work when the angle here is acute. This is basically because if you can't have an angle here that's too big, because say it was 92 degrees, then 92 plus 90 exceeds 180. So you can see that we cannot put an angle that big in this situation. So these equations are quite limiting. So in other words, as it stands currently, we don't have a way of interpreting what this will mean when the angle here is rather big. So what we want to achieve is to generalize this notion of trigonometry to much bigger angles and to any angle we like, and be able to interpret and calculate what this thing means. So there's kind of two motivations as to why we want to make this generalization in the first place. First motivation is kind of just, well, for its own sake. Because it's kind of weird to be able to say like, oh, I know how to do cosine of like 80 degrees, 89 degrees, and then suddenly say like cosine of 92 degrees, well, we don't know how to interpret that and we don't know how to deal with that. So that's a bit strange. We want to improve upon that and be able to deal with any sort of angle we like. And the second motivation actually has something to do with rotations. So rotations are obviously something we want to be able to describe. And it turns out trigonometry is actually not about triangles like these definitions lead you to believe. Trigonometry is actually really more about circles, and by the time we make this generalization, you'll see that trigonometry is really a tool that is used to describe rotations. Okay, so let's see a rotation situation. So let's say we got a point that's rotating on a unit circle like this. First, just the notion of unit circle. What that means is just the circle centered at the origin, and it has a radius of 1. And a key question you want to be able to answer is, well, as this point rotates around this unit circle, how do we keep track and sort of describe the location of this rotating point? So here's a fixed snapshot of that previous animation. So the point was traveling around, but let's say it lands here at some point. What we can do to begin trying to locate this point, one way to do that is to draw the following arrow, okay? So we're going to draw an arrow that starts from the origin, and it's going to point right at the point there. Once this arrow is drawn, we can look at the following angle. So the angle that's between the arrow we just drawn and the positive x-axis. And you can see that just providing this theta, this angle here, you can see that we're providing like a sense of where this rotating point will be. Like if I told you this angle as a number, you have a good idea where it will be on the circle. So theta sort of gives the angular position of this point. And also that angle there is important for this reason too, because you can see that how fast the point rotates around the point sort of is determined by how fast this angle itself changes. So how fast this angle changes dictates the speed at which you rotate. So that's another reason why looking at that angle is important. Okay, so look, I just want the location of this point, right? So of course there's another way to do it, and that's just the good old way of just telling me the x and y coordinates of this point. So an important question is, how do we connect these two ways of measuring the location together? And that is, if we know theta, how do we find the values of x and y, the actual coordinates of this point in the number plane? So in other words, what's the connection between these three polynomials? Okay, so we can begin to try and find that relationship by firstly drawing in this triangle here. And you can see that if this point here is x and y, if this is the coordinates, the y is just how tall it is. So you can see that the y coordinate is also describing how long this red length is going to be. And similarly, the x coordinate here describes how long this length is going to be. Once you've drawn this triangle, what's our goal? We're trying to connect these three polynomials together, right? And at the same time, if you look at this right angle triangle here, hopefully you can see that we can just do the simple right angle trigonometry to try and begin connect these three polynomials together. Oh, and by the way, if we were trying to do that trig ratios business, we need this length as well at some point. And just a reminder, we're looking at a unit circle here. So the length of this arrow is really the radius too. So it's just the length of 1. Okay, so we're going to begin looking at cosine of the angle first. So cosine theta is going to be adjacent over hypotenuse. So we get x over 1. But over 1 does nothing, so I might as well just write cosine theta is just x. Similar thing, we're going to look at sine of theta. So sine of theta is opposite over hypotenuse. Y over 1. Again, the 1 is useless, so just sine theta is y. We saw 2 trig ratios. Let's look at the last one. We're going to look at tan. Tan theta is going to be opposite over adjacent, so y over x. Okay, so let's clear away the working out and just focus on these 3 main equations we just arrived on. So we pretty much answered this question. You can see that the connection between these 3 polynomials are actually really simple. They just connected to each other through these trigonometric ratios. And you should definitely interpret this result simply in words like so. So cosine of theta is just giving us the x coordinate of this point here. And when you look at this angle and you do the sine of it, the sine of this angle will return exactly the y coordinate over here. Okay, so what's a similar conclusion here for tan? Like we could just say like tan theta is just all y on x algebraically. But these two are sort of nice physical interpretations. There's kind of like a physical interpretation to it. Like it's the x coordinate of this location, y coordinate of this location. So instead of just saying y over x is tan, is there like also a physical interpretation to what this is? Well, there is. If you look back at this triangle here, you'll see that y on x is really the rise over the run. And it's the rise over run of this segment here. So you can see that rise over run will give us the gradient. So in actual fact, the y on x is actually giving us the gradient of our arrow over here. Okay, so let's do a quick recap of what we just saw. So we got this point that's rotating on a unit circle, and we're trying to find its location. And we began by drawing this arrow here from the origin up to the point. And we saw this theta that describes the angular position of the point. And then we were also like, I just want to find the x and y coordinates at this point to describe where it is. And then we did a bunch of trigonometry to realize that if we take simply the cosine of this angle here, then that will retrieve and give you the x coordinate that we're after here. And similarly, you look at this angle, and then if you take the sine of this particular angle, then that's going to return and give us the y coordinate. And lastly, tan. For this angle here, if you take the tan of this angle, then you will get the gradient or the slope of this arrow. So these realizations and interpretations are actually perfect for our generalization purpose, where we try to generalize trigonometry to any angle of any sizes we like Like before, in the right angle scenario, we couldn't do it because in a right angle triangle, you're limited to having just acute angles, right? But here, we don't have this restriction, right? You can see that in this scenario, if I want to work with a bigger angle, what can I do? I can just simply let this point like rotate on. If I just let it spin to this quadrant, you can see that when I want to say like it's reached here, it's got some x and y coordinates. And this drawing the angle as well. So again, drawing to get the angle, you gotta get the arrow first. So draw the arrow from the origin up to the point. And then remembering we're gonna measure the angle with respect to the arrow itself and also the positive x-axis. So here you can see that the angle is a much bigger one. It's 150 degrees. So you can see that in this scenario, we are able to talk about any angle we like. And then we're just going to reapply the interpretation and the understanding we got previously, and then use that to define the values of the trig ratios under these different angles. So we're just going to say, oh, we have an interpretation and a way to look at what cosine of 150 represents now. It's nothing more than just the x-coordinate of this point. And similarly, sine is going to give us the y-coordinate over there. Okay, so we have the right interpretation, and then we just got to go calculate and figure out a way of actually getting these coordinates, okay? Oh, and tan, of course, give us the slope here. The slope of this arrow. Okay, so let's calculate these. Let's try and attempt to calculate these three items. We'll go for the cosine first. Remember, so we got an angle 150 here. Cosine 150 will just give us this x-coordinate. And we're just trying to find the x-coordinate right now. Well, visually, you can see that the x-coordinate is a number sitting here on the left side of the whole number plane. So firstly, we'll acknowledge that whatever this x-coordinate number is, it's actually a negative number, right? So being on the left side of the number plane. So whatever that x-coordinate is a negative number. Well, negative of what number? Like, what is the size of that number? You can see that the size of that number is exactly this physical horizontal distance here. So our job is to find exactly how long this is. And hopefully you can see how we can achieve that. If you want this length, a good place to focus on is this right angle triangle over here. And inside this right angle triangle, we can see the notion of that related angle starting to kick in. So this is our related angle from the previous lesson. And it's 30 degrees here. Okay, we just need a few more things. So now, again, focusing on this right angle triangle, if we look at the cosine of this related angle, what are we going to get? We're going to get adjacent over hypotenuse. And adjacent is that horizontal distance. And well, the hypotenuse is this length here. But again, remember we're sitting in on a unit circle with a radius of 1. So this length of hypotenuse is exactly 1. So over 1, we can just not write over the 1. You can see that the conclusion from here is that the horizontal distance that we're after is nothing more than the cosine of the related angle. Okay, so putting this information in here, we found the horizontal distance is cos of 30. Okay, so cos of 30, we know that from our exact value table, and it's root 3 on 2. And that's it. Final answer to cos 150 degrees is the negative of this fraction. Okay, so that's cosine taken care of. Oh, this is just the exact value and then a rough decimal. And you can see that it's pretty reasonable because we're quite close to -1. So this being roughly minus 0.866 looks about right. Okay, let's go after the y-coordinate now. Well, first we acknowledge that the y-coordinate will sit here, somewhere along here in the y-axis. So you can see that it's definitely a positive number. So we can acknowledge that. So sine 150 is going to be some positive number. But what's the size of that number? The size of that number is controlled by how tall this distance is. So you can see that also we're going to look at the same right angle triangle as before. It's also helpful in this situation as well. And again, that related angle. But now what allows us to get at this vertical distance is the sine. If we look at the sine of this 30 degrees. So sine of 30 is going to be opposite side, which is our vertical distance over the hypotenuse, which is the length of 1. And we come to the conclusion that the vertical distance we're after is also just sine 30. Placing this in here. Remembering that sine 30 is just half. And that's our final answer. Okay, lastly for tan, we're going to try and do tan of 150. But what's the interpretation for tan? Tan will give us the gradient of this arrow here. But notice how, because it's sloped and orientated like this, we know that as a final number, the gradient number is going to be negative when the line is sloped like this. So we acknowledge that it's some negative number. But negative of what? It's the negative of the rise over the run here. Again, looking at this right angle triangle with that 30 degrees, you can see that tan of this 30 will give us exactly rise over run. So we can make that substitution. The rise over run is tan of 30 degrees. And tan of 30 is 1 over 3. Okay, so these are the three quantities we just found, all in a diagram together. The x and y coordinates and the gradient of our arrow here. And here's all the working out we just went through in all three of the calculations. So you can begin to see a pattern behind what we're doing. Essentially, there are kind of two steps to trying to find these values. Firstly, we've got to elect whether it's positive or negative, depending on whether the x and y coordinates are positive or whether or not the gradients are sloped positively or negatively. So based on those features, we choose a plus or minus. And then we always seem to be doing the same trig ratio, and then we also need to take the related angle. So whenever you're trying to calculate one of these two things, we've got two steps we've got to do. Choose plus or minus, and find what the related angle should be. We can kind of summarize that as like a general formula. So cosine of any angle, choose a plus or minus, and then it will be cos of whatever the related angle is in that situation. And of course, similar results for sine and tan. Okay, so we're going to look into more about how do we make this choice of that plus or minus, depending on which quadrant we're in. So we're going to look at quadrant by quadrant. So here's the first quadrant. So you can see that if you're in the first quadrant, sort of everything is positive. The x-coordinate is a positive number, so is y. And the gradient being tilted like so is a positive gradient. So you can see that all the trig ratios, because cosine gives the x-coordinate, sine gives the y-coordinate, they're all positive, along with tan. So as a summary, we sort of call this quadrant 1. We refer to that as quadrant A as well. A just stands for all, again saying all the trigonometric ratios for the angle in this quadrant are all positive numbers. Let's flow over to quadrant 2. In that like the previous example we just saw. You can see that the y-coordinate is positive. That implies sine is positive. But suddenly the x-coordinate is a number lying over here. So that's a negative number there. And the gradient, the tilt of this is negative, so tan is negative. So notice that, look at all three possibilities. The only one that's positive is sine. So we refer to quadrant 2 as the S quadrant, saying that the sine ratio here is the only one that's positive, and every other ratio is negative. Okay, so that's the first two quadrants, and then have a look at the other two and verify whether these quantities are positive or negative for yourself. And you can see that in quadrant 3, only the tan ratio is positive, so therefore it's the T quadrant. And in the last one, you can see that only the x coordinate, which is what cosine works out, that's the only positive quantity, and everything else is negative. So that's going to be the C quadrant. So altogether, I can remember this as the ASTC diagram. It just tells you whether the trig ratios are positive or negative. And some people like to remember this as all stations to central. Okay, so here's a summary of absolutely everything we just covered in one slide, along with the animation of all the angles. We're going to flow through all the angles, and then you can check out the respective cosine value, the x coordinate, the y coordinate giving us the sine value, and the tan value here that gives us the slope of the arrow as we rotate around.